5.1 Mathematical Induction. In general, mathematical induction can be used to prove statements that assert that P of n is true for all positive integer n, where P of n is a propositional function. A proof by mathematical induction has two parts: a basic step, where we show that P of 1 is true, and an inductive step, where we show that for all positive integer k, if P of k is true, then P of k plus 1 is true. Here we have this repeated. Why mathematical induction is valid? Suppose we know that P of 1 is true, and that the proposition if P of k then P of k plus 1 is true for all positive integers k. To show that P of n must be true for all positive integers n, we use a proof by contradiction. Assume that there is at least one positive integer for which P of n is false. Then the set S of positive integers for which P of n is false is not empty. By well-ordering property, S has a least element, which we'll denote by m. We know that m cannot be 1 because P of 1 is true. Because m is positive and greater than 1, m minus 1 is positive, a positive integer. Furthermore, because m minus 1 is less than m, it is not in S. Recall that m was the smallest integer in S. So m minus 1 is not in S. So P of m minus 1 must be true. Because the conditional proposition P of m minus 1, if P of m minus 1, then P of m is also true, it must be the case that P of m is true. This contradicts the choice of m. Hence, P of n must be true for every positive integer n. As we noted, mathematical induction is not a tool for finding theorems about all positive integers. Rather, it is a proof method for proving such results once they are conjectured. In example 2, using mathematical induction to prove a summation formula, we'll both formulate and then prove the conjecture. Conjecture formula for the sum of the first n positive odd integers, then prove your conjecture using mathematical induction. The sum of the first n positive odd integers for n equals 1, 2, 3, 4, 5. These sums are 1 plus 3, which is 4. 4 is 2 squared. 1 plus 3 plus 5, this is 9, 3 squared. 1 plus 3 plus 4 plus 7, this is 16. This is 4 squared. 1 plus 3 plus 5 plus 7 plus 9, the first 5 odd positive integers add up to 25, and this is 5 squared. So I conjecture that the sum of the first n positive integers is n squared. The first n positive integers, that sum is equal to this. The nth positive integer is 2n minus 1. The second is 1 plus 2, 2 times 1. The third odd positive integer is 5, which is 1 plus 2 times 2. So the end will be 1 plus 2 times n minus 1, which is 2n minus 1. Let P of n denote the proposition that the sum of the first n positive integers is n squared. Our conjecture is then that P of n is true for all positive integers n. To use mathematical induction to prove this conjecture, we must first complete the basic step, that is, must show that P of 1 is true. Then we must carry out the inductive step, that is, show that P of k plus 1 is true when P of k is true. We now attempt to complete these two steps. P of 1 states that the sum of the first odd positive integers it is just 1, so 1 squared. 1 is equal to 1 squared. We know that this is true. Inductive step. Show that if P of k, then P of k plus 1 is true for every positive integer k. To do this, we first assume that the inductive hypothesis P of k is true for an arbitrary positive integer k. That is, we assume that this sum is true for arbitrarily chosen k. We must show that if P of k is true, then P of k plus 1 is true. Then this conditional proposition will be true. What is P of k plus 1? The sum of the first k plus 1 odd positive integers is equal to k plus 1 squared. It follows that the left-hand side is equal to, we separate the last term to k plus 1. The sum of the first k odd numbers is k squared by assumption, which is P of k. And this is k squared plus 2k plus 1, which is k plus 1 squared. This shows that P of k plus 1 follows from P of k. It is, we have shown that P of 1 is true and that the conditional proposition, if P of k, then P of k plus 1 is true for all positive integer k. Consequently, by the principle of mathematical induction, we can conclude that P of n is true for all positive integers n. That is, we know that the sum of the first n positive integers is equal to n squared for all positive integers n. The next example, the harmonic numbers h sub j for j equals 1, 2, 3, and so on are defined by this equals d. For instance, h4 is this sum, and if we add up these fractions, you'll get 25 over 12. Use mathematical induction to show that h with index 2 to the n is greater than or equal to 1 plus n divided by 2. Whenever n is a non-negative integer. To carry out the proof, let P of n be the proposition, then h with index 2 to the power n is greater than or equal to 1 plus n over 2. We have to complete these two steps. Basic step, P of 0 is true. P of 0 is h with index 2 to the 0 equals greater than or equal to 1 plus 0 over 2. That is replace here n with 0 on both sides. But h with index 2 to the 0 is just h1. So we have a true inequality here. The basic step is checked. Inductive step. The inductive hypothesis is the statement that P of k is true. That is, h with index 2 to the k is greater than or equal to 1 plus k over 2, where k is an arbitrary non-negative integer. We must show that if P of k is true, then P of k plus 1 is also true. P of k plus 1 is just this inequality. H with index 2 to the k plus 1 is greater than or equal to 1 plus k plus 1 over 2. And just replace here on both sides k with k plus 1, you get this inequality. Assuming the inductive hypothesis P of k, it follows that h with index 2 to the k plus 1, which is this sum by definition, is equal to the sum of the first several terms up to here. So the sum of these terms is h with index 2 to the k, and then we write down the remaining terms. Here the denominator is 2 to the k plus 1. In the next fraction we'll have 2 to the k plus 2, and it continues like that. The last denominator can be written as 2 to the k plus 2 to the k. That is, we have 2 to the k fractions added here. We write this inequality because of the assumption hypothesis h 2 to the k is greater than or equal to 1 plus k over 2, and then these terms are copied, and then each denominator is replaced by the last denominator. When we increase the denominator, a fraction decreases. So we obtain even smaller sum, because we have 2 to the k fractions here, and each of them is replaced with 1 over 2 to the k plus 1, we have this inequality. But this is just 1/2. And taking these two fractions, we get 1 plus k plus 1 over 2, which is, so we prove that h in index 2 to the k plus 1 is greater than or equal to 1 plus k plus 1 over 2, which is just p of k plus 1. We have completed the basic step and the inductive step. Thus, by mathematical induction, P of n is true for all non-negative integers n. That is, the inequality for the harmonic numbers holds for all non-negative integers n. The inequality establishes that the harmonic series, this is infinite series, diverges because the partial sum increases with n. The partial sum is h with index n, and it increases because h with index 2 to the n increases indefinitely.